What is going on, everybody? It's Medicosis Perfectionalis. Welcome back to my statistics playlist. In previous videos, we talked about an introduction to statistics, the difference between the independent variable and the dependent variable. We talked about quantitative variables versus qualitative variables, the numerical and the categorical. We discussed continuous variables, discrete variables, ordinal variables, and nominal variables. We also talked about the measures of central tendency, such as the mean, the median, and the mode. Today, we will dig deep into the Pearson's correlation coefficient, usually referred to as lowercase r. What does correlation mean? It means a relation between two variables or two data sets. Here's one variable, here's the other variable, here's the relation between the two. It could be a positive correlation or a negative correlation. Click the like button, click the subscribe button, and let's get started. This is my statistics playlist. Please watch these videos in order for maximum understanding and retention. The field of statistics can be broadly divided into descriptive statistics and inferential statistics, otherwise known as inductive statistics. If you are familiar with induction in philosophy, it's a very similar process. Induction rather than deduction is the method most commonly used in science. Descriptive statistics is going to describe and summarize a given sample of data quantitatively, and this is done in a lab, on your computer, etc. All of this is fun and games, but it doesn't tell you how the real world is. What if we can take a random sample, which is a small sample, and if the sample is randomized and representative, we can take these results and infer. By means of induction, we can learn about the population in the real world. But remember, your sample has to be random and representative. But if your sample is just from one hospital, you cannot say, oh, everyone is sick, therefore every person in the general public is sick. Well, this might be true if you spend most of your time on social media, but that's not reality. Not every person in the public is sick, but every patient in the hospital is sick. That's why they are in the hospital in the first place. If you wish to see more videos like this in the future, please drop your favorite math symbol emoji in the comments. Let's focus more on descriptive statistics. Descriptive statistics is further subdivided into description of conditional distribution. We don't care about this today. And the quantitative measures of dependence, where you have a variable dependent on another variable. This is today's topic. The quantitative measures of dependence are further subdivided into the famous Spearman's rho and the infamous Pearson's R. Today, we are talking about Pearson's R. There are some differences between Spearman's rho and Pearson's R. One of them is that Spearman's has to have one or both variables as continuous variables. But in Pearson's, the two variables should be continuous. But what the hell is a continuous variable? I am glad you asked. If you have watched my statistics video titled Quantitative Variables versus Qualitative Variables, you shall recall that quantitative variables are the numerical ones, whereas qualitative variables are the categorical ones. The former deal with numbers, whereas the latter deal with categories, labels, or names. Numerical variables could be continuous variables or discrete variables, whereas categorical variables are ordinal or nominal. A continuous variable is a variable that deals with numbers and where your possibilities are endless. For example, the weight of something or someone. That weight could be 0.2 kilograms, it could be 0.5, it could be 0.5554, it could be 0.59, it could be 200 kilograms, 201 kilograms, 202.5 kilograms, for 10,001 kilograms ad infinitum. It could be any numerical value. This is a continuous variable. If you wish to download these doozy colorful notes, go to medicosisperfectionalis.com. I help you learn, understand, and pass exams. If you want me to personally tutor you, reach out to me on my website. Another concept that you should be familiar with is the difference between dependent variables and independent variables, and I have a separate video on this topic in this statistics playlist. Let's review. Recall that you have a cause and an effect. The cause happens first before the effect. Causes lead to effects, and effects have causes. The cause is the independent variable, whereas the effect is the dependent variable, because the effect depends upon the cause. For instance, I punch you in the face and then you start to bleed. Of course, I will never do this because I love you. The punching is the cause. The bleeding is the effect. Independent variable versus dependent variable. Let's say that there is a correlation between the number of hours of studying and the test score. Usually we draw the independent variable on the horizontal axis and the dependent variable on the vertical axis, because the dependent variable depends on the independent variable. And because this is a straight line going up, the more hours you study, the higher your test score. It's a positive correlation. How about this one? F around and find out. The cause and the effect. Independent variable, dependent variable. And if the line is horizontal and going up like this, it means that the more you F around, the more you find out. Let's say that cigarette smoking causes small cell lung cancer. Where is the independent variable? Cigarette smoking. Where is the dependent variable? Small cell lung cancer, because it's dependent on the other variable. In my video titled Data Visualization, we have talked about scatter plots. Just like these, a bunch of points scattered. That's why it's a scattered plot. What are the pros of using a scatter plot? You can deal with two variables and you can see if an outlier exists. What is a statistical outlier? It's the weirdo, statistically speaking. Disadvantages of using the scatter plot is that it's not very good for very large sets of data, and don't forget that even if x and y are correlated with one another, this doesn't necessarily mean that x caused y. And it doesn't mean that y caused x. Correlation is not the same as causation. Here's a scatter plot. All right, here's x, here is y. Independent variable, dependent variable. And this is a positive correlation. The greater the x, the greater the y. It's a positive correlation. How about here? Oh, the greater the x, the lesser the y. It's a negative correlation. Would you like me to draw an outlier for you? How about something like this? Oh, that's the weirdo. That's a statistical outlier, because all the points are here around that line, and this one is weird. It's an outlier. Here's a question for the statistics connoisseurs out there. Which of the following is the least affected by outliers? Is it A, the mean, B, the median, or C, the mode of the sample? Let me know the answer in the comments. But if the points are scattered all over the place haphazardly like this, with no pattern whatsoever, then we say that there is no correlation between the x variable and the y variable. Enters Pearson's correlation coefficient, or lowercase r. What does it do? It measures the linear correlation, emphasis on the word linear, between two variables, the x variable and the y variable. Do you remember this? Oh, the positive correlation? Yes, the r is positive 1. Okay, it's positive at least. I can understand that. How about the negative correlation? The r is negative 1. It's as if this graph is a reflection or a mirror image to that graph, assuming that we have a vertical mirror. How about here when there is no linear correlation between x and y? R equals 0. Null. Does anyone remember the null hypothesis? Yeah, what does the null hypothesis say? The null hypothesis says that there is no correlation between this variable and the other variable. To learn more about the null hypothesis, check out my video titled The Null Hypothesis, which you can find in this statistics playlist. But what does it mean that the Pearson's correlation coefficient can measure the linear correlation with regards to direction and strength? Let's start with direction. It's easy. If it's a positive direction, we give it a positive number. If it's in the reverse or the opposite direction or the negative direction, we're gonna give it a negative value. So you know the direction by the sign of the R. But how about the strength? You know the strength from the value of the r. It's like a scalar versus vector in physics. There is the magnitude and there is the direction. Magnitude, direction. Please refer to my physics playlist. How can we tell whether the positive correlation is strong or weak? From the value of the r, from the magnitude of the r. When the correlation is solidly positive or strongly positive, r is positive 1. That's the perfect positive correlation. But what if the correlation is positive but weaker? Because the stars are not aligned as much when it comes to the direction of the straight line. Well, then the correlation is still positive but weaker, meaning the number is less than 1. Still positive, still greater than 0, but less than positive 1. What if the correlation is even weaker than that? Then the value is smaller. Still positive, but smaller. There are a couple of urban myths that we need to debunk. Myth number 1. A student saw this graph, saw the x variable and the y variable, and saw that the points are scattered all over the place and that r is about 0. Okay, this is true. Let's assume that r is perfectly 0. The student then argued, therefore there is no correlation between x and y variables. This is a load of rubbish. Just because Pearson's correlation coefficient is 0 doesn't necessarily mean that no relation exists between the x variable and the y variable. What does it mean then? R equals 0 means that there is no linear correlation between x and y, because not every correlation is linear. There could be a correlation that is nonlinear. So the moral of the story is Pearson's correlation coefficient only cares about the linear correlation between the two variables. Urban myth number 2. Upon looking at the relation between the shoe size of a person and the net worth of the same person, the student argued, I hereby declare that an increase in shoe size causes an increase in net worth. But that's another load of rubbish. A young lad asked Warren Buffett, hey, how can I invest my money wisely? The Oracle of Omaha replied, rule number 1, don't lose money. Rule number 2, don't forget rule number 1. A student asked Medicosis, how can I become good at statistics? Rule number 1, correlation is not the same as causation. Rule number 2 of statistics, please refer back to rule number 1. Correlation is not the same as causation. Just because on this stupid graph there was a positive correlation between the shoe size and the net worth, this doesn't necessarily mean that one caused the other. Correlation is not the same as causation. And for the pros, you know why this graph looks like this? It's not that the increased shoe size is gonna make you richer, but the greater the shoe size, the greater the likelihood that you're not a baby. And of course, adults have more money than kids, which means the results of this study are confounded by age. Age is a confounder. Age is what determined the net worth in this case and not the shoe size per se. How can we calculate the Pearson's correlation coefficient? Tell me about the math. Before I tell you about the math, let me tell you about the concept. This is Pearson's correlation coefficient of a sample. It equals the covariance of the two variables, the x variable and the y variable, divided by the product of their standard deviation, meaning the standard deviation of x multiplied by the standard deviation of y. Look, anytime we divide by the standard deviation, anytime we take the standard deviation into consideration, the value is set to be normalized. What the hell is that? To belabor this point, because it's worth belaboring, we're gonna talk about the normal distribution curve, also known as the bell-shaped curve, also known as the Gaussian curve. And let's imagine that we're talking about IQ. IQ of a population follows a normal distribution curve. This is the central tendency, and because this is a perfect normal distribution curve, it is not skewed one bit, therefore this middle value represents the mean, it also represents the median, and it also represents the mode. I can say that if the curve is a normal distribution. So this is the mean. Okay, what's the standard deviation of the mean? You can go up, you can go down. You can go one standard deviation above or one standard deviation below. You can go another standard deviation above and another standard deviation below, etc. One standard deviation is called 1 sigma. 2 standard deviations are called 2 sigma. 3 standard deviations, 3 sigma, etc. But when you go below the mean, it's -1 sigma, -2 sigma, or -3 sigma. The mean of IQ in a population is 100 by definition. One standard deviation is about 15 points. So, if your IQ is 1 standard deviation above the mean, it means that your IQ is 115, because 100 mean plus 15, 1 standard deviation, equals 115. So let's say that hypothetically your IQ is 115 right now. And let's imagine that we can figure out some way to measure the IQ of your great-great-great-great-great-grandfather back in the golden days when dinosaurs walked the back of the earth, when your grandfather's generation had to walk to school every day for 39 kilometers every single day, barefooted with an inflamed abscess under their calcaneus. We're gonna measure your grandfather's IQ, and it was also 115. Therefore, the doofus student concludes, therefore, I am as intelligent as my grandfather. And this is the third load of rubbish. No, this does not mean that. Why is this? Because the population today is not the same as the population 200 years ago. People today are smarter than people 200 days ago. I know this is hard to believe, especially if you log into LinkedIn, or as they call it in France, LinkedIn, a site where people smell their own farts and they like it. It's monkey say, monkey do on steroids. But hey, Medicosis, if my IQ is 115 and the IQ of my great-great-great-great-great-grandfather is also 115, what's the problem of deducing that we are both equally smart? The problem is that today's population is smarter than yesterday's population, which means that you are probably smarter than your grandfather when it comes to IQ. Because as the population gets smarter and smarter and smarter, statisticians have to renorm the data so that the mean of the population has to equal 100. Oh wow, the mean of the population of every population is always 100. This is not a coincidence. It's a part of the definition. It is necessarily true. The mean of the population has to equal 100. So every time the population gets smarter, we renorm the data. Every time the population gets dumber, we have to renorm the data again so that the mean is exactly 100. So can I conclude anything when I see that my IQ is 115 and my grandfather's IQ is also 115? Yes, you can deduce that you are 1 standard deviation above the mean of your cohort today, whereas your great-great-great-great-great-grandfather was also 1 standard deviation above the mean of his cohort 200 years ago or something. But this does not mean that the average individual today has the same IQ as the average individual 200 years ago. Always ask yourself, compared to what? That's why we call it standard deviation. It's the deviation standardized based on your cohort. And that's why whenever you take standard deviation into the equation, you are said to be normalized. This is how we know that your IQ is 1 standard deviation above the mean and your great-great-great-great-great-grandfather's IQ was also 1 standard deviation above the mean because the data is normalized. Again, Pearson's correlation coefficient of a sample equals the covariance of the two variables divided by the product of their standard deviation. The covariance of the two variables is this. What are the two variables? The x variable and the y variable. Why do we subtract? Because it's the difference from the mean. Remember that all of statistics can be summarized as central tendency, right smack in the middle, and variation on the extremes, to the left and to the right. That's why we subtract. Next, the product of their standard deviation. This is the standard deviation of the x variable, and this is the standard deviation of the y variable. You multiply the standard deviation of the x variable by the standard deviation of the y variable. What if I remove this square root? What is the name of this? This is called variance. Therefore, standard deviation is the square root of variance. And why do we subtract again? Because the standard deviation deviates from the mean. You can deviate above the mean or deviate below the mean. Please do not confuse R with rho. R is the correlation coefficient of the sample, whereas rho is the correlation coefficient of the population. The way I remember this is that I imagine the rho as a letter P because they look very similar. And this is a great example of how you can take a normal sample from the comfort of your room, descriptive statistics, and then infer from that what's going to happen to the population as a whole, inferential statistics. As is the habit towards the end of each video, we have a question for you. Here's a graph, x here, y there, and a bunch of dots. If you have to pick a number for r, do you think r is A, positive 1, B, negative 1, C, positive 0.4, D, negative 0.4, or E, 0? Please let me know the answer in the comments. You will find the exact answer in the next video. Don't forget to watch my statistics playlist. In the next video, I'll teach you how to use this equation with a real-life example. If you value what I do, help me make more videos by supporting the channel. Go to buymeacoffee.com/medicosis. There are more than 700 premium videos available on this channel when you click the join button and choose the highest tier. Please subscribe, hit the bell, smash like, support my channel on Patreon, PayPal, or Venmo. Go to my website to download my courses, notes, and cases, or if you would like me to personally tutor you. Be safe, stay happy, study hard. This is Medicosis Perfectionalis, where medicine, chemistry, math, and physics make perfect sense.